All right, so we're back here now. Let's talk about acids and bases, the types of acids and bases. The first piece that I want to talk about is strong acids and bases, okay? So we've talked about strong acids, strong bases before, but let's remind ourselves about these. Strong acids, right? Essentially, we want to see, hey, how stable is that conjugate base? So our strong acids, we have HBr, HI, HCl, right? If we think about the conjugate bases of these, right, we have Cl minus, Br minus, I minus, right? These are really electronegative elements, and they're pretty large, right? They're large electronegative elements. So this H plus, right, is going to be lost pretty easily because large electronegative, right, it's going to be stable. It's going to be very stable conjugate base, okay? Then our other strong acids, we think of HNO3. Let's think about HNO3 for a second. If we think about it, NO3, let's draw our Lewis diagram, right? Here's our Lewis diagram. We have, let's get our charge on there, -1, right? We have resonance structures. We have 3 of them, 3 resonance structures for NO3 1 minus ion, okay? So it's a very stable conjugate base. So then the acid is going to be very strong, right? It's going to almost completely ionize in water, okay? So that's what we say is with strong acids, strong bases, completely ionizes in water, okay? Next one that is very strong, HClO4. Same exact idea, right? We have Cl in the center. It's got oxygens all the way around it. And we have a resonance structure. We have 4 resonance structures here. Again, this anion, or the conjugate base of our strong acid, right, this is really stable. So it's going to lose that H plus really easily, okay? Finally, we have H2SO4. H2SO4, same idea. It's going to lose one of those hydrogens. And again, we end up with lots of resonance structures, right? We're going to have 3 resonance structures there. So again, the resonance structures stabilizes the conjugate base, which means that the acid is going to be really strong. So that means that if we were to write out our reaction, right, these, when they dissociate in water, essentially they're completely favoring that dissociation. So we would write out that HCl plus H2O goes completely, essentially, over to H3O plus and Cl minus, okay? So those are our strong acids. Let's get our strong bases. Strong bases, essentially, we're going to say group 1 or 2 hydroxides. So that would be lithium hydroxide, sodium hydroxide, potassium hydroxide, right? And then we've got magnesium hydroxide. All of these, right, they are going to completely dissociate in water. They completely split up, and they release OH minus, right? So it is going to become a proton acceptor there, right? So these are strong bases. They completely split up. We get lots of OH minus, okay? All right, let's talk about our weak acids and bases then. So weak acids and bases, right, we generally think about 2 things. Weak acids, we oftentimes think about carboxylic acids. So carboxylic acids are something that have, oh, I'm off the page up at the top, something like this, right, where this hydrogen is going to be lost, right? But it's not super strong, okay? It's not going to completely dissociate in water, okay? So those are oftentimes what we think about. This shows up fairly often on the AP test, right? This would be a carbon in the center here. This is an R group. This shows up a lot in biology as well, okay? For bases, we oftentimes think of nitrogen bases, okay? So this would be something like ammonia that we talked about before, but that nitrogen could be in any of our compounds, okay? Again, this shows up in biology a fair bit, okay? So Ka and pKa, right? Ka is the equilibrium constant for the acid dissociation, okay? So last unit we talked about the equilibrium constants, the equilibrium expressions. It's the same exact idea, but now we're applying it to our acids, okay? So let's look at our example here, okay? So our example, we have HF plus H2O. Oops, I screwed that up. I got to fix that. F minus and H3O plus, right? HF would be our acid. This is going to be our base. This is going to be our conjugate base and our conjugate acid, okay? So HF is not a strong acid, okay? HF is not a strong acid because hydrogen can get pretty close to fluorine, so it's just not as stable. That F minus is not as stable, okay? So let's write our Ka value. Ka expression would be, well, concentration of F minus times the concentration of H3O plus divided by the concentration of HF. Right? H2O, of course, doesn't show up. So this is kind of the general form, of our acids, right? The equilibrium expression for our acids is always going to be the base. So let's do it, we'll do it as A, maybe A minus, times the concentration of H3O plus, because we're doing this in water, divided by HA, okay? This is our general form of our equilibrium expression, okay? So in some ways, this is a little bit easier than last unit with our equilibriums. Hey, that's great. Okay, of course then, if we have a Ka, we can calculate pKa. pKa would be the negative log of the Ka value, right? Just the same as the negative log of our of our pH, right? All of that. It's all the same relationship, mathematical relationship. Okay, so on here, we're going to do a problem with this. If we know the Ka value, right, we should be able to calculate Kb. We should be able to calculate what happens, okay? So the Ka value, which would be the reaction as it goes this way, Ka is going to be equal to 6.9 times 10 to the minus fourth, okay? The Kb value would really just be the opposite way, all right? So the Kb value, again, back to our previous page here, right? Ka, oh, I didn't put this on our previous page. That would be part of why. So Kw is going to be equal to Ka times Kb, all right? Because we have acids and bases going into water, okay? So Kb, right, we would take, we know Ka, Kw is 1 times 10 to the minus 14th. We divide and we're going to get Kb. Kb is equal to 1.4 times 10 to the minus 11th, okay? All right, so now if we have we have a question, something like this, right? What is the pH of 0.1 molar NaF, right? This would be a solid, an ionic solid that we could toss in. NaF It's a sodium salt, so it's going to be totally soluble. We'll get all this F minus, but then that F minus is going to react with water. So we have essentially the opposite reaction here, right? We are going to have F minus plus H2O. This is going to be in equilibrium with HF and OH minus, okay? So our initial value for F minus would be 0.1. H2O we don't care about. HF initially is 0, and our OH minus, we're going to say that it's essentially 0, right? Yeah, it's 1 times 10 to the minus 7th. It's close enough, all right? Real small. Our change, we're going to lose x, minus x there. We're going to gain x up here, and we're going to gain OH minus, okay? Finally, our equilibrium would be 0.1 minus x. This is going to be plus x, and this is going to be plus x, okay? So now let's solve this. We know our Kb value, which is, right, the base with water. So Kb, 1.4 times 10 to the minus 11th equals our products, well, that would be x times x divided by 0.1 minus x. So again, same idea as last unit. We're going to kind of ignore this here, and now we can solve for it, okay? So if we go ahead and solve for it, I can't remember what number we get. I'll solve that, and then I'll come back in a second.